We are really glad you're here joining us. If you are here to hear about the Virtual Learning Lab, you're in the right place. My name is Phil Pokert. I'm the director of the University of Florida's Lastinger Center and project director of the Virtual Learning Lab. This is a session entitled Precision Education, Lessons Learned from the Virtual Learning Lab, which was a center funded by the Institute of Education Sciences. And so wanted to just share with you a little bit about the event purpose as we get started. But before I do, wanted to invite everybody to just introduce themselves in the chat. And so you can find the chat at the very bottom of your Zoom screen. I'm sure you know by now. If you could go ahead and just open it up and introduce yourself by including your name, your role, your organizational affiliation, and just out of curiosity, where are you dialing in from right now? And so go ahead and put those in, and we'd love to hear from everyone to see who we have in this Zoom room with us. And we'll go ahead and get started in just a moment. All right, really wonderful to see everybody coming in from all over the country and even other countries. Hello, Canada. So we're really glad that we have this wonderful group, and just wanted to give you a sense of what we're up to with this event. This is just a high-level showcase of a range of research that has come out of this center grant from the Institute of Education Sciences. It's taken place over the last 5 years. So you're going to see a summary of a wide variety of research from a number of different investigators. We're hoping that this conversation, the presentations that you'll hear from 9 different researchers will stimulate further research and development in the field so that we aim to have folks build upon our work and continue to expand in the learning, engineering, and sciences. Of course, I want to just make sure that there's a disclaimer that the research reported here was supported by the IES and U.S. Department of Education through a grant to the University of Florida, but the opinions expressed are those of the authors and do not represent the views of the Institute or the U.S. Department of Education. So we're going to begin by hearing from our program officer, Erin Higgins, and then when she's finished, I'll come back and introduce you to the researchers that you're going to be hearing from in just a moment. So Erin, why don't you go ahead and take it away.
Great, thanks, Phil. So thanks for joining us today. I'm Erin Higgins, and I'm the program officer at IES, who has been working closely with the Virtual Learning Lab team for the past 5 years. And I just wanted to take a few moments to reflect back on what we at IES had envisioned for this center when we started planning for it actually about 7 years ago. So we funded the center in 2016, and the goal was really to try to explore how we could best use large amounts of data generated from these widely used digital learning platforms to improve instructional practices, content, and learning tools that are provided to students within those platforms. We also had the goal of providing national leadership and outreach in this rapidly growing area of work. At the time we put out the call for proposals, many public and private funders, including IES, have made substantial investments in educational technology. And specifically at the time, IES had actually invested in over 100 individual research projects reflecting the diversity of educational technologies available at the time. But none of those investments in R&D had focused on how to combine these massive data sets from large digital learning platforms with administrative data from states and local education agencies to understand how we can improve students' experiences with these platforms. And at the same time, you had all these other scientific fields exploring the ways in which machine learning and other analytic methods emerging from data science could lead to novel insights. And they were seeing success in those endeavors. So at that time, it was right, I think, for us to put out this grant competition to explore the value of research at the intersection of education technology and data science to see what it could do for education practice. And so we were thrilled when the virtual learning lab team, which was the University of Florida, University of Colorado Boulder, now Arizona State, in partnership with developers at StudyEdge and the state of Florida's Department of Education, alongside many districts, pulled together this proposal that set out to do exactly that. So it was incredibly important, innovative work to see how we could leverage these large amounts of data from education technology and state administrative data records to personalize instruction for students. And the team, interestingly, has not only thought about ways to improve students' academic progression, but also to think about how to better engage students with the system and get them back on track when they've disengaged. So this approach to figuring out how to personalize students' experiences within a digital learning platform, which is what you'll hear more about today, is really exciting and innovative, and there have been many lessons learned along the way. I think one of the biggest strengths of the center has been the well-established partnership between researchers, industry, and school district and state leaders. And without these partnerships in place, this research would not have happened. So moving forward, I think we see this as a strong model for how to put these partnerships together. And we are excited to hear more about the important findings that have come out of the past 5 years of work, as well as to build off of that by continuing to invest in research in this digital learning platform space. We have a research network competition, which we will announce the outcome of later this summer, as well as an X Prize announced earlier this year focused on similar efforts. And so with that, again, thanks for joining us today to hear more about this research, and I hope you enjoy the session.
All right, thank you so much for those kind words, Erin. Really appreciate that and setting us off on this event. And so I wanted to just transition us quickly right into the rest of it. And so you'll see here a list of 9 different presentations. Each of them will be about 5 minutes long. And then we're going to have a 2-minute question and answer session open to the floor. In terms of how to engage the presenters in the Q&A aspects of it, we certainly invite you to go ahead and use the chat while they're presenting. And then I can certainly moderate those questions to the presenters during the 2 minutes. If we don't have any in the chat, we certainly welcome you to unmute your microphone and just go ahead and speak during that 2-minute Q&A session as well. But would appreciate if everyone stays on mute when you're not speaking and not presenting so that we don't have any of the background noise. So you'll see these presentation topics here, and then we're going to begin with a presentation from the principal investigator at the University of Florida. And you'll see the list of the different partner presentations from, as Erin said, University of Colorado Boulder, Arizona State, and UC Santa Barbara. And so we'll look forward to just moving us through. We will take a 5-minute break about halfway through so everyone can take a moment to stretch. But we'll go ahead and just get right to it by turning the mic over to Walter Leachy from the University of Florida, who'll be presenting on the video recommendation system for algebra.
Hello, everybody. I will share my screen here. And okay. Okay, so I will give you a very quick overview of where we are and where we are going next with the main study of the Virtual Learning Lab, which is about the video recommendation system for algebra implemented in Algebra Nation. So we used Algebra Nation, which is now rebranded as Math Nation because it has more than algebra, it has geometry too. We used it as the platform for evaluating recommendation system, but also as the platform for our studies on virtual learning. And so the idea here was to develop a system that would recommend videos, as you're seeing this screen here, that would pop up with showing which video the student should see next. Algebra Nation has a lot of videos, 93 main videos, and then lots of other review videos. And they're organized in 10 sections, and each section has between 6 and 12 topics. Students, typically go between watching videos, doing review videos, and doing quizzes. So we want to incorporate both estimating their knowledge and engagement in this recommendation. So this is a high-level flow chart. Algebra Nation is used by teachers in the schools. In some districts, it's the curriculum. And so a section is usually takes a teacher 1 or 2 weeks to go through it. At the beginning, the students take a pre-test. We use that to estimate student ability using item response theory. Then students either watch a video that they choose on their own, or they go straight to taking a quiz. This is about, I think, 50-50 here that they go and take a quiz. And then based on the response to the quiz, we estimate ability with item response theory again, and estimate engagement with an algorithm developed by Ciri Di Mello at UC Boulder, who is a co-PI in this project. Then we recommend a clip or a whole video, and if they watch it, then they can take a quiz, and then the cycle continues again. I'm not going to go very specifics here on the algorithms. We used data mining methods to create weights for each video, and then provide with the student the video that would maximize the probability of improvement in knowledge. Now, and then after they finish a section, that is a post-test, which is our proximal outcome. The distal outcome is the high stakes Florida algebra and, of course, exam. Now, we did last year, well, we have done, last year we did a field experiment, very large, with almost 20,000 students. Now we started on February 3rd, and as you know, COVID hit us at some point. So after 6 weeks, on March 17th, schools closed. However, we did get some promising results from just 6 weeks, looking at just the post tests, and then we found a small but statistically significant effect. HG is 0.07, which is about 20% of mean gain. And then we did look at what happened after schools closed, but there wasn't any effect after schools closed. We did survey the teachers extensively to understand how they changed the instruction after schools closed, and we hope to be able to publish an interesting paper on that. Now, so where we go from here, we just finished a longer replication of the experiment. So from November 24th, 2020 to June 1st. And we are interested in several questions. These are some. Are there larger effects with longer exposures? Do students use the system differently? Do some students with some backgrounds benefit more, or using some self-regulated learning strategies? And then we also ultimately looking at fairness and equity implications of using personalization strategies such as this one. Okay, so that's my very high level overview. Please feel free to contact me if you'd like to learn more details.
And we have a couple of minutes for any questions that might come from our audience. I see there's one in the chat already. If you want to respond, Walter, what was the comparison of learning gains between students who didn't use the platform versus students who did?
No, the comparison was, so it was a design where students within teachers were assigned to either treatment or control recommenders. So they were both, it was blind to students. So both treatment and control students were seeing recommended videos. The treatment use, the recommended videos were picked with our algorithm. Control, the recommended videos were picked as just the next video in the scope and sequence. So it is, not comparing against no recommendation. It's comparing two different ways of getting a recommendation.
And there's another question in the chat. Was the larger replication done with students in person, remotely, or both?
Both. We recruited teachers and assigned all students within classrooms. Some teachers were teaching 100% face-to-face, some teachers were teaching 100% remotely, and some were doing both.
Wonderful. Thank you. 30 seconds left. If there's any other questions. You mentioned a flow chart. It was one of the slides within the presentation. Did you want to say more?
Yes, yes, that was a simplified flow chart. I mean, I have a more technical one too. If you are interested, you can email me for that.
Oh, you only saw one slide.
Yeah,
Did everyone else see the slides? Okay, all right. Just want to make sure we don't have a technical glitch. We certainly can provide the slides. Okay. Maybe it's Jim Salzman, Walter, if you want to perhaps share the file. I will keep us moving. We do have another question in the chat, Walter, if you want to take it on the chat from Lena, and that might be wonderful. But I'm going to keep us moving with our second presentation. Thank you very much, Walter, for going first. And that's second presentation is from Guojing Zhao at the University of Colorado Boulder. The title of the presentation is Reinforcement Learning for Enhancing Collaborative Problem Solving. And so, Guojing, you want to go ahead and share your screen and take it away?
Yeah, sure. So, so my name is Guojing Zhou. I'm a postdoc working at University of Colorado Boulder. My talk is about our plan to use reinforcement learning to enhance student collaboration, collaborative problem-solving behavior. We focus on the context where students working collaboratively on educational video game while room meetings. This screenshot shows a scenario where 3 students were working together on an educational game, which is called Physics Playground. The game was running on one student's computer and shared to the other 2 while the screen sharing feature of Zoom. So only one student has the control of the game, and we call this student the controller. The other 2 students contribute to the collaborative problem-solving procedures through making verbal contributions, so we call the other 2 people contributors. The goal of the game is to move the ball to the balloon. Everything in this game obeys the basic physics laws, and students can make objects of any shape to move the ball. Our goal for this research work is to encourage students to talk more and equally during their collaborations. And our method is to use reinforced learning to induce our collaboration support policy that can provide real-time collaboration suggestions. Here shows the procedure of our research, which includes 4 steps. First, we analyze student collaboration data to identify the impactful events that can encourage students to talk more and equally. Second, we formalize student collaboration as a marker of decision process. And then we will apply reinforced learning to induce collaboration support policies, and finally, we will evaluate our reinforced learning policies. Currently, we are still working on the 2 steps, so I will talk more about these 2 steps. Our data includes information from multiple modalities, including video, audio, eye tracking, and game logs. As our major goal is to encourage students to talk more equally, we mainly focus on the data that describe students' communications and their in-game operations. The verbal communication data are transcriptions of the audio recordings of each team member, and the transcriptions were segmented into utterances. We annotated the utterances with indicators about counters. Some example indicators are response to others' ideas and provide reasons to support a solution. There are 14 indicators in total. Besides verbal communications, we are also interested in the game logs as they provide context behind students' verbal communications. For example, the game logs allow us to know when students added a new object and when they made a problem-solving attempt. Remember that our goal for this work is to our goal for the analysis is to identify impactful events that can encourage students to talk more equally. And the events are basically students' use of indicators. Actually, the indicators that occur in students' communication. Towards this goal, we segmented our speech sequences into small chunks of around 10 seconds. And we describe the students' communication in each chunk using the indicators mentioned before. In order to analyze how the indicators may impact students' participation in the game, we built linear regression models that use indicators in one chunk to predict students' verbal participation in the next one. Currently, we are still working on the data analysis and haven't reached any conclusions yet. In order to apply reinforced learning, we need to formalize student interaction as a mark of the decision process. Basically, we need to organize student collaboration data into a sequence of states, actions, and rewards. In our plan, the states are features that describe the current collaboration and problem-solving state. The actions are the impactful events determined by the data analysis, and rewards are changes of student participation in the game. For example, a positive reward for an increase of participation and a negative reward for a decrease of it. Once the MDP is ready, we will apply reinforced learning to induce our collaboration support policies that can give real-time collaboration suggestions. And we will evaluate our reinforced learning policies using both offline and empirical approaches. That's all for my talk. I am happy to answer any questions that you may have.
Thank you very much. So we have about 2 minutes for questions from the audience. There's one in the chat. Was there any specific reward provided to distinguish different types of participation rather than just positive, negative?
Do you mean the rewards?
It does say specific reward.
Yeah. Actually, we are still working on this question. We are actually still working on the question that how to define student participation. We have tried some definitions, but it does not work well. As our goal is to encourage students to participate more, and we actually prefer to use like more specific numerical rewards rather than positive and negative.
Wonderful. And the follow-up question was any weights, any types of weighting? Or
yeah, good question. So for weightings, I assume that weighting for the participation. Again, we are still working on a question, but for example, there are many ways to define student participation: the number of words produced by each student, the number of active time, things like that. So we are still working on it, and but I'm sure that using some type of way will help us define a better reward model for the reinforcement.
wonderful. Well, thank you very much. I think that brings us to the end of the 2 minutes, and I don't see any other questions, but certainly welcome anybody to continue to engage in the chat with coaching. Thank you very much for the presentation. And so we are going to keep things moving. And next we will be hearing from Dr. Danielle McNamara, who was a co-PI on the project from Arizona State University. Her presentation is titled Natural Language Processing for VLE Research. And so go ahead, Danielle, and take it away.
All right. I think I'm sharing my screen now. Is that, am I sharing my screen now? Great.
Yes, you are. Yes, you are.
Thank you. So I'm going to give a general overview on natural language processing for VLE research. And then Jenny Shin is going to give some an overview of, or a snippet of some of the findings that we've had in our analyses in this particular project. So first, I want to break down the terms. I'm pretty sure that if you're here, you know what a virtual learning environment is. And frankly, I copied this from Wikipedia. So as you see, it's pretty general. Any online platform, it can encapsulate any online course, reading resources, informational sites. So it's pretty broad when we talk about virtual learning. And of course, you know, we've had a lot of experience with leaving the classrooms and moving more toward these virtual learning environments, particularly over the last decade or so, and in particular in the last year. So it's pretty broad as to what kinds of environments we're talking about. The second, what is NLP? So very broadly, natural language processing, for people who in the audience who may not be familiar with it, is the use of computational programs to simulate the understanding or use of human language. So it was the movement from just computer languages to understanding natural language. And it's the programs that are written in order to understand the use of natural language. So to break it down, there are many approaches to natural language. One is just the words. So when we just use the words, many people use the words, the n-grams, bags of words, and they might take the n-grams and look at the latent aspect of the words or their embeddings using various programs. Historically, LSA was one of the first, LDA, and then Word2Vec, and now BERT. And then there are additional, many complex ways of looking at word embeddings, but this is mainly the semantics. We tend to also look at linguistics. So computational linguistics looks at features of words and sentences and psycholinguistic properties. So each word might have a naming time, and then you use those psycholinguistic properties to predict the aspects of words. So what's behind the words? So we look at word associations, syntax, cohesion, various aspects that are related to and use computational linguistics. And then you combine that with machine learning. So various machine learning, including deep learning methods to understand the use of language. And so power of computational linguistics in combination with machine learning. So one of the things to recognize, discourse involves complex cognitive and social processes, and we can use computational linguistics that integrate language across multiple levels. And this provides a means of better understanding how humans construct and represent meaning in the world. So few would dispute that language and communication are important in classrooms. I think we have experience in classrooms and we use language. We also use our body and we use visuals, but people are talking. However, language and communication are not often ignored in VLEs. It's devoid of the aspects of language and communication that are used in the classroom. You might have, particularly in math, you can get a lot out of math performance. And so those communications and those interactions often ignore the interaction parts and the language of the student. So, but language and communication are obviously crucial, and they're crucial to learning and even math. And so that's what brought us to this project in working with Math Nation and Algebra Nation in better understanding various impacts of and how can we use the language of the student and the tutor to better understand what's going on in these interactions. So how can we use it potentially to improve the algorithm that Walter talked about? Or how can we use it to, how can we use our understanding of language and communication to help the teachers more and help the tutors in various ways? And so before Jenny talks about some specific results, I just wanted to talk about roles for natural language processing in virtual learning environments. I'm going to talk about 5 ways that natural language processing has been used in the past in and currently in virtual learning environments to kind of give you the lay of the land of the kinds of work that's being done right now. So a very typical use of natural language processing in virtual learning environments is automated feedback. So you have a student here who is entering some kind of language. You apply natural language processing, there's an algorithm, and that provides feedback. So there are many systems that do that. A very classic one, one of the first was AutoTutor. iStart is a system that my team has built in order to help students learn comprehension strategies. And one way to think about it is that there are many automated writing evaluation systems. We've developed the Writing Pal, but these, where they're taking language from the student and they are giving feedback to the student using fairly complex pedagogical algorithms as well. Another is communication with the learner. A lot of you have experienced this just on the phone. You call a business, and then a system tries to recognize what you're saying. You ask a question, it gives an answer. In learning systems, another classical one, I'll bring up AutoTutor again, where the pedagogical agent is answering questions for the student and then giving feedback as well, but it's that communication with the learner. And there are also many systems that have pedagogical agents that their role is to communicate with the learner and attempt to understand what the student needs along the way. Another more recent use of natural language processing is under modeling communication among learners. So we can look at the networks among learners. A standard approach is to look just to see if they are interacting. Another more complicated approach is to look at the nature of that interaction. So for example, in cohesion network analysis, we define these links between these students in terms of the cohesion or the association between the links, but you can use other methods as well. And so this is an interesting approach in understanding the dynamics of communication and collaboration among learners, particularly when they are in environments such as chat environments. And of course, one of the endpoints is we are attempting to model and predict learning. So using the language of the learner, even in math environments, we've been able to use natural language processing to understand the underlying skills of the learners and predict the probability of whether they'll complete, for example, a MOOC course. And in math courses, we have been able to successfully predict the probability of passing courses even for students in middle school. And so that's one of the projects that we've been working on in the virtual learning lab, is working to examine the extent to which we can use language to augment these models to predict learning. Another approach that we've been using is to use natural language processing to predict learners' skills, knowledges, and attitudes. If you can think about this as kind of a reverse engineering, we take output from the student, and such as an essay or explanations or summaries that they may have written, and we might have an external measure of their skills, knowledge, or attitudes, and then we use those models to see if we can predict their skills and knowledge, and produce something that can augment, again, the models, but also produce to help with stealth assessments while students are in VLEs. So this is kind of a summary of what I wanted to talk about today, very broadly. And I don't want to say language and communication should not be ignored in VLEs, but I'd say they need not be ignored. And that if you are creating a VLE, I would encourage you to think about how to analyze and use the language that the students are producing and capitalize on the power of natural language processing. A shameless plug to a new journal, Technology, Mind, and Behavior. Please check it out. It's particularly relevant to this conference. And there we go. And in the next show, Jenny Shin will describe a snippet of her natural language processing research in the VLL.
Thank you so much, Danielle. Really appreciate that. And so any questions from the audience? I have another minute or so. All right, curious about how multilingual and or non-native English speakers are taken into consideration.
Oh, heavily. We've across the years done quite a few analyses on the differences between first language and second language speakers. And there are differences, and for the most part, I'd say that depending on the context, often the algorithms can either take that into consideration or still work. It's one of the things we've looked at pretty extensively, but we've also created algorithms just for second language learners. So it's a very interesting avenue of research.
Right, another from John. Do you see NLP as a supplement or a replacement for clickstream analysis? Could you speak about the advantages or limitations of NLP compared to that data?
Oh, thank you, John. I realized that when I clicked onto the next slide that I forgot to say that, and I was like, well, I'm not going to back up. But yes, of course, John. One of the more exciting, I view things as multidimensional, and language is one of the dimensions. And so in many of our analyses, in moving on, there's a couple of papers by Scott Crosley where it's combining this information of the clickstream, other aspects of what they're doing, so their emotions, their, whatever kind of information you have. And I think a most interesting avenue of research is to examine, what's the minimum amount of data that you need, or how can you get multiple aspects of information from the students so you can build a more complete model. But no, I don't view language as the end all. I just really encourage people to look at language in addition to clickstream, since that's much more common.
Yeah, thank you, Danielle. I just wanted to jump in and just say that seems to be a really powerful way to think of this, especially framing this as the power of big data and the power of the data collected by these platforms. There's estimations that there's something like 5 times the amount of data in language as there is in clickstream. So it's both quantitatively and qualitatively, I think, more powerful. It'd be interesting to think about, to me, maybe it's already been done, but I'd love to see that, to think about how this enhances the kind of inferences that we can gain, or how difficult it is to get some of those things from just clickstream data, because I've tried, and you probably tried, and and how much further this can take us along, being a neat kind of methodological approach. Thank you.
Oh, yeah, thank you for that, John. And also, I'll say that my strong interpretation of natural language processing and the linguistic side of it is that I do truly believe that, the words that the students are saying or the tutors are saying gives a picture of the neural activity. Even I will go so far that the words and the context of the words is a way of understanding how people are thinking about things. And that's why I think that even a few words, if we keep moving along, I mean, there's limits to this. I mean, if they only say, can you give me that homework assignment? Only so much we can get from that. But the more that we understand what we can get from language, and particularly in combination with what they're doing and why they're doing it, and the clickstream data, I think is a very, very important avenue of research.
Wonderful. Thank you very much, Danielle. I see that there's a couple of more questions for you in the chat, and so maybe we just handle those. It sounds like a fun continuation around foul, derogatory, and harmful language, and colloquial versus standard language. But I'll let you take that offline to keep us moving and allow our other presenters, because we do want to hear from Ginny Shin, who joined the project as an extern working with Danielle at Arizona State, and has since agreed to join the faculty here at the University of Florida. And so you see her title for her presentation, and go ahead. Ginny. Oh, we lost.
I forgot to mute myself.
There we go. Yes, we can see them now.
Yeah. So thank you, Danielle, for your amazing introduction. I think that really shapes my talk very well. So I'll now be sharing more specific findings where we attempted to identify pedagogical conversational patterns in VLE. So like we all experienced last year, more than a year and a half now, student engagement in online learning can be very difficult. And one of the big reasons why is because we're losing that face-to-face quality in classroom and trying to provide interventions immediately to the student by the reactions that students are giving face-to-face. So in order to overcome this, a lot of online learning environments have identified different ways to incorporate different interactive activities, motivating students with more personalized goals and activities. And also, like Walter mentioned, recommending right videos based on their ability level and their preferences. Those has been adapted to online learning environments to really make learning in online more engaging, despite the fact that you don't really have a teacher in front of you. But one aspect, like Danielle alluded to, is that we haven't really looked into further in terms of how the effective communication between the tutor, online tutor, and the students are currently happening, and whether the tutors are making any intentional effort and attempt to close this gap, physical gap with the student, and then trying to really make their online lessons and the activity more engaging. So there comes our study. So here we focused on looking into whether we can identify pedagogical conversation patterns, especially from online learning video, online algebra learning videos. So we used the Math Nations data where there were 5 study experts who were covering various algebra topics, 25 different algebra topics in lecture videos. And our research question was specifically to look into whether the Math Nations tutors are using different strategy of language choices or any pedagogical discourse pattern so they could better establish communication and more engaging communication with the students. So like you can imagine in the video, the tutor will be explaining some concept about the function here. And then he might be greeting you like, oh, hey, Algebra Nation, today we'll go through this. So he'll explain the topic a little bit. And then halfway through, if you're having a trouble, he'll probably sharing attitudes like, oh, I know this is very difficult for me as well. And also providing encouragement to the student like, you got this, there you go, you're solving this correctly. So those type of intentional language choices and their pedagogical communication patterns, so those are the ones that we target to extract and identify automatically using natural language processing. So the analysis was conducted in 3 stages. So first of all, we identified we constructed a statistical language model with unsupervised machine learning algorithm to identify the communication component from the lecture videos. So we analyzed a total of 125 video lecture from Math Nations now, and then automatically identify that 22% on average of each tutor's lecture video were allocated for communication. So here I'll define the communication a little bit more. So we define the communication component as where the tutor is trying to encourage student, greet student, structure their lecture that has nothing, that doesn't have a direct connections to the content or any of the workbook they're provided to explain to the students. Once we identify this 22% of their lecture video, which are communication component, we use the 2 advanced computational tools, linguistic tools, Cometrics and Seance, to see if the tutors are actually making intentional word choices in this communication component and whether they differ in terms of their sentiment behind those word choices. And what we identified using 125 video from 5 different tutors is that we could actually explain and correctly identify the right tutor based on their language choices to the 87% accuracy using machine learning algorithm. And finally, to provide a more theoretical background to our findings, we looked into the pedagogical discourse marker core functional framework by Fung and Carter, 2007, trying to see if there's any intentional and functional differences between these language choices the tutors are making. For example, tutors are, some of the language choices and intentional word choices that tutors are making could have some interpersonal functions. For example, trying to make your lecture more interpersonal. It could also have a structural function where you're trying to guide the students and making sure that students are understanding the topic is changing or that they're moving on to different topics. And finally, asking rhetorical question or asking hypothetical question to the students so students could do more cognitive related activities. So as you can see, once you identify the communication component, you can see that there weren't that many systematic patterns that was identified between 5 tutors in terms of how much communication component they're providing in each lecture topics. As you can see, the x-axis is 125 videos across these 25 different algebra topics. But on the other hand, when you're looking at the workbook component, where the tutors are rephrasing the workbook component, the questionnaire that's provided in the workbook, or trying to explain the lecture to the student, there is a very specific patterns that you can identify as they're moving along to different chapters. Then we identify 17 different clusters of their pedagogical communication pattern that these 5 tutors are using very commonly across this 125 different videos. Then we identify whether that maps onto the theoretical framework of whether these specific cluster of communication pattern has any interpersonal, structural, or cognitive functions to make their communication more encouraging and interactive. And you can see the showing responses, for example, when students are when the tutor is asking a question and then they're providing responses immediately. That was one of the most popular interpersonal function the tutors are using, followed by some structural function, for example, denoting that the topic is closing and opening to the student explicitly, and also providing explanation when the topic is shifting. And after we did the analysis and got the finding that we could actually automatically understand and extract the communication component from these tutoring videos, we try to expand our findings to see if we could successfully identify these common communicative strategies in Algebra 101 tutoring setting as well. So likewise, we are looking into how tutors are different in terms of their communication. So we expanded to whether the students and the tutors and their interaction of it could be also identified using NLP. And also we're currently working on trying to see if it could automatically detect any important language evidence and linguistic differences that students are using in an algebra discussion board as well. Yeah, and that's the end of the presentation. And I'd like to provide special thanks to my collaborator, Renu and Michelle.
Wonderful. Thank you so much, Ginny. I want to take just a minute to keep us moving for any questions that the audience may have. So go ahead and populate them in the chat and we'll keep things moving. All right, a question about, is there any difficulty with accents?
That's a good question. So we analyzed the data that was transcribed professionally, but if you were to analyze the voice data, that would definitely be something to look into as well. And that would definitely increase the difficulty of the analysis, but also it would make the finding more interesting to look into as well.
Thank you. All right, so we'll invite anyone to have any additional questions to continue in the chat. And of course, we'll have a little bit of time at the end too to entertain additional questions. Thank you very much for the presentation, Ginny. I'm going to turn it over to another colleague at the University of Florida, Anne Corinne Huggins-Manley, who's going to be presenting on scaling items and persons for obtaining ability estimates in VLEs. So moving on from the NLP work into a different kind of data analysis. Take it away, Corinne.
Hi, thank you, Phil. Let me start the slides. I hope everybody can see. I'm going to be presenting a study titled A Semi-Supervised Learning Method to Adjust Biased Item Difficulty Estimates Caused by Non-Ignorable Missingness in Virtual Learning Environments. So it's a mouthful, but there's a lot of info there if it is helpful. I do want to note that the first author of this is an extern of the Virtual Learning Lab. He couldn't be here today, but I advised him, and we also have our PI, Dr. Leche, on this project. So the purpose really here is we've got a lot of assessment items in the Algebra Nation or Math Nation platform, and we didn't know coming into this project how hard those items were. We know that they were written to be aligned with certain standards which have certain levels of difficulty, but ultimately there are a lot of things like the distractors in the items and the cognitive complexity of the items that can result in different hardness or easiness than we thought. And ultimately we have about 400 something items between the two main types of tests. So we really needed to know how hard our items are. And we needed to know that because how can we estimate student ability if we don't know how difficult the items are? So I have a picture here of a person jumping over hurdles that are increasing in size. And this comes from Howard Weiner uses hurdles a lot to talk about different features of testing. But the reality is we can evaluate this person's jumping ability because we know the hurdle height and we can see the ordering of the hurdles, so their relative height as well. So if he jumps over that last big one, we know more than if he just jumps over the first small one. But imagine if we didn't know the hurdle height, if we just knew how many hurdles he jumped over, like 2 or 3 or 4. That would be similar to adding up the correct answers on these test items in our platform and saying the student got an 85% on this assessment, or the student got 4 out of 5 items right. But without knowing how difficult the items are, it would be like if we didn't know if these hurdles were 1 inch tall or 10 feet tall in trying to gauge his jumping ability in front of us. So for us to infer student ability from the student item responses on all these assessment items, we have to know how hard the items are at a bare minimum. And you might say, well, why do we need to even estimate ability? Well, in our project, just like many others, we need ability in a lot of different places to personalize. So this is a different version of the chart that Walter Leche showed at the beginning of today's session. So there's a little more in here, but it's the same flow. And I've highlighted here all the places where our ability estimates matter. And so if we're using something like what we call the total test score, saying this student got 3 out of 4 items right, we are always going to have this problem that we really don't know much more than how many items they got right. Just like we wouldn't know how well somebody can jump just by knowing how many hurdles they went over. We need to know how hard those item hurdles are. So for this study, there are many methods available for estimating item difficulty. They go back many decades, even a century at this point. But none of those methods have really been fully evaluated in virtual learning environment data, in which we have both non-ignorable missingness. So the missing data on assessments is related to a lot of other variables about the students. And also we have a lot of missingness. So on average in one of our domain areas, such as quadratic formulas or whatever, we might have up to 90% of students giving no data on those assessment items. So the purpose of this study was to implement a semi-supervised learning method to estimate unbiased item difficulties for all the Algebra Nation practice test items. So for our method, we started by first doing a really thorough investigation of what's going on with the missing data. And we identified that there were at least 3 types of missing item responses. And we ended up modeling them in a tree-based logistic regression. So you can see a little bit in this figure. But ultimately, most skipping of items was either because the student skipped the domain, so they never even engaged in that area of algebra, and hence they didn't take the items, or they didn't complete a domain. They were working in that area of algebra and then they stopped, and so they didn't answer all the items, or they just skipped an item that was shown to them. And so each of these different types of missingness had a different relationship to the actual item data itself. So we then, after we learned what those relationships were, did our best job to estimate them, we then applied semi-supervised deep learning methods to obtain unbiased ability estimates. And we did that by making use of a set of students that we called anchor students. We do have some students who completed all item response data, so that was a feature that we made use of. Oh, and there's a little diagram about some of the stuff about the deep learning method. And then after doing that, we knew a lot about ability at that point, and that allowed us to know more about item difficulty. So we performed some final adjustments to the item difficulty, and we used 2 methods, an equating method and also more of a bootstrapping approach. So here's a lot of findings. I'm going to walk through one of them, one right in the middle, either the quadratics, but I'll do quadratics part 2 here. The red line represents an unbiased estimate. It's at 0 there for the amount or for the bias. So we want our estimates to be on that red line. And as you can see, for the original estimates, before we did the adjustments, they were mostly positively biased. And those are for the item difficulties. But as we did the 2 types of adjustment, we saw a reduction in bias. And in fact, it was really the bootstrapping method that resulted in the least amount of bias in the different item difficulty estimates, and also the least amount of variance in those estimates and how much bias they might have. So in this study, we developed and demonstrated an approach to obtain unbiased item difficulty estimates and virtual learning environment data without a formal large pilot that could control more for missing data. And this allows for more advanced measurement approaches underlying VLE algorithms. I hope people can make use of this so that we aren't using so many of the total test scores, which falls in line with that adding up how many hurdles somebody jumped over without knowing anything about the hurdles. But there's a lot of things we don't know. How do we deal with more complex item types? There's a reason we worked with the binary items only. It's the method's a lot more intractable, but with more methods, we'll get better for items scored polytomously. We also aren't sure yet how to best investigate invariance in these item properties. And this is critical for matters of fairness. But to get them was one chunk, and now we have to figure out how fair those estimates are. And also, what would one do if they didn't have anchor students that were highly engaged in answering all the items? We had some other ideas for methods, but our method that we proposed made use of that specific feature that maybe not everybody has. And that is all.
Wonderful. Thank you so much, Corinne. Certainly I want to invite a couple of questions from the audience. seeing any questions come through. And so.
Oh, I do see one.
Oh,
And yeah, the answer there is yes. So we are in what we call an item response theory framework. And one benefit to that framework over something like classical test theory would be the independence of the item parameters to various samples, and also that includes the independence to the particular sample of students. I will say though that our students that were the anchor students were in general of higher ability than others. And so even in that framework, we still have to do adjustments to get the truly independent values. Otherwise, we just get large standard errors. So the sample can affect it in that sense.
Wonderful. So we are going to go ahead and take a very brief break. And so I'm going to invite everybody to just go stretch for a moment. We'll come back together at 5:05 p.m. or 5 past the hour, wherever you may be in the country. It's 5 past the hour, and so I just want to welcome everybody back. We have 4 more presentations that we're going to be hearing from a number of different researchers on the project. The next one up is a doctoral student of Dr. Huggins Manley, whom you just heard from, and that is Ziying Li. And so Ziying will be presenting on measuring student ability from single and multiple attempt practice assessments and VLEs. And so would you go ahead and take it away, Ziying?
Oh, sorry. Could you give me a permission to share my screen?
Oops, I just stopped sharing that. You should be able to do it now. Apologies.
Okay. It's fine. Nice. Okay, can you see my screen? All
Yes,
right.
we can. Go ahead.
So today I want to share our research topic about measuring students' ability from single and multiple attempt practice assessment in virtual learning environments. As we know, virtual learning environment allows students to select the practice item at their own description. And it means that some of the students may select the same items multiple times, and thus it leads to the multiple attempts data set contains with single attempts response and multiple attempts responses. So we are thinking about whether we could evaluate students' ability with this kind of multiple attempts data set from virtual learning environment. Our research question primarily focused on the estimated bias of students' ability when the dataset contains a proportion of students making multiple attempts. Also, we consider whether there is interaction effect of sample size and the number of answer items. In our study, we conducted a simulation research. Also, we selected the sequential 2PL IRT model in our research. Now, let's see what we found. In this figure, the x-axis is the number of answer items, and the y-axis is the bias. We are looking for the bias to be 0. It means that no bias. We can precisely estimate students' ability. For the lines with different colors, they refers to the sample size. And we should also notice that the 0.2, 0.4, 0.6, and 0.8, and also the 1, they represent the proportion of students making multiple attempts. For example, 0.4 means there is 40% of students making multiple attempts. So we can see that even though the proportion of students making multiple attempts changed, the trajectory for each sample size are almost similar under these conditions. We can conclude that the sequential 2PL IRT model can estimate students' ability no matter what proportion of the students making multiple attempts. Also, we can find that there is an interaction effect of the sample size and the number of answer items. Let's set this figure as an example. When the sample size is 5,000, the blue dotted line, we can see the buyer is 0. When the student, even though the student answer 5 items, we can precisely estimate the student's abilities. When the sample size is 1,000 or 500, the bias tends to 0 as the number of answer items increases. Finally, we can conclude that the sequential 2PL IRT model has a good performance in estimating students' ability, even though the dataset misses with the single attempts and multiple attempts item response data. For the large sample size, like 5,000, we don't need to worry about the number of answer items. The number of answer items can be small. If we have the sample size is 1,000 or less, we can try to reduce the bias by increasing the number of answer items. For example, like looking back this figure, when our sample size is 1,000, we can increase the number of response items from 5 items to 10 items, or even to the 15 items or more, so that we can reduce the estimate bias. In the future studies, let's thinking about these 2 questions. If we collected the multiple attempts data that is complete with a short-term response rather than a long-term study, can the sequential 2PL IRT model continue to perform well for estimating students' ability? Or if we change our test items format, like change the multiple choices item to the open-ended item test, can the sequential 2PL IRT model precisely estimate students' ability? So there are very interesting topics in the future. So it's all my presentation for today. Thank you for listening.
Wonderful. Thank you very much, Ziying. So invite a question or 2 from the audience, please. All right, we have one. How do you estimate bias?
Yes, we conducted a simulation study. So at the beginning, we have randomly generate the student's ability as the true ability. And then after fit our data to the sequential 2PL IRT model, we can get the estimated ability, and thus calculating the differences between these 2 values, we can get the bias. So that's what we did.
All right, thank you. Any other questions before we turn it over to Sanaz Nazari? Okay. Well, thank you very much, Ziying. We really appreciate your presentation. Thank you for the questions. And so we're going to be hearing next, also from the University of Florida, Sanaz Nazari, detecting careless responding to assessment items in VLEs.
Hi, everyone. Thank you. So do you see my screen?
Yes, we do.
Okay, great. Okay. The project I'm going to talk about is, just let me see. I have a hard time with this. Okay.
We can see your screen well.
Yeah, I have a lot of buttons in on my screen. I cannot see. Okay, sorry.
It's okay.
The project I'm going to talk about is detecting careless responding to assessment items using person-fit indices and a random forest. Careless responding. Informative assessments within virtual learning environments. It's very hard to keep students motivated across different tests, and this lack of motivation may result in careless responding, which in turn may produce bias in the student ability estimates and threat validity of conclusions. Among several proposed methods to detect careless responding, we chose response time and time thresholds for true careless responding in ROC curves, and also person-fit indices, parametric or non-parametric. There is a wide range of them, and also each index can capture person misfit from a different perspective. So the goal was to use multiple person-fit indices simultaneously, which is possible by machine learning classifiers such as random forest. So the research question was, does the use of person-fit indices as features in a random forest to detect careless responding outperform the use of person-fit indices by method? Participants were 14,474 students from Algebra 1, and our measure was 10-item assessment of linear and quadratic functions in Algebra 1. For analysis, we computed 14 person-fit indices of perfect package for all the students in the sample, and 3 best indices were chosen as predictors of the random forest. And for parametric person-fit indices, we used 2PL model. Additional predictors were item difficulty and discrimination parameters, number of items answered by each student, and number of correct items answered. For carelessness identification, the time taken to answer each item was recorded, and by comparing the graph of correct responses versus incorrect responses, empirical cutoffs were determined. For evaluation, we used area under the curve of an ROC curve to measure the accuracy of predictions by person-fit indices and other predictors as features of a random forest. The selected person-fit indices according to the best AUC were Batman errors with 54.7%, agreement statistic with 69.1%, and dependability statistic with 63.5%. The AUC showed that random forests with those specified predictors improved the classification. So as you see, we have a 77.2, and the best person-fit index for area under the curve, we had agreement statistic with 69.1, and random forest improved the classification. And this 77.2 is an acceptable test to distinguish between careless and non-careless responses. Implications. By introducing random forest, careless responding can be conceptualized as an item-person interaction rather than a static person feature by just using person-fit indices. And also, when we use person-fit indices to capture carelessness, sometimes the true positive rates against false positive rate may swing and cancel out and end up in a very low area under the curve, which is no discrimination. But random forest doesn't have this problem because of the way trees are constructed. For future research, we would have a trained random forest model that will be available to detect carelessness in the form of an R package for applied researchers. They could enter the raw data and obtain a prediction of careless or non-careless for each single item in their test, and then they can decide how they would like to aggregate and interpret carelessness according to the context of their research. Thank you very much. Any questions?
Wonderful, really appreciate that. Thank you very much. All right, invite questions from the audience for a minute or two. All right, well, we call that wait time in the education business. So giving folks a moment to pause and reflect. Really appreciate your presentation. If a question does come up, certainly you can populate it into the chat, and you can see that Christine has given you Sanas Nazari's email address, so you can contact directly. And so really appreciate it. We're going to be turning now to a presentation from Daniel Katz at the University of California, Santa Barbara, Personalization, Content Exposure, and Fairness in Assessment. Go ahead and take it away, please.
Okay. 1 second here, sorry. Cool. You all see my screen?
Yes, we can. Thank you.
Cool. Sorry. First of all, thanks for coming. The title of my talk is Personalization, Content Exposure, and Fairness in Assessment. I am a graduate student at UC Santa Barbara, and I've been an extern for the Virtual Learning Lab, where I owe very much a lot of thanks to Corinne Huggins-Manley and Walter Leet. And as I've been working with them over the past year and a half now or something like that. When I first started talking to Corinne, we started looking and thinking about, I guess, what is now MathNation, and sort of merging the technical considerations that we've heard a lot about here with some of the educational testing realm. And in the educational testing realm, we work with the standards for educational and psychological testing, which I'm sure many people here know about. And it's effectively sort of the guidelines or, well, standards for any test or assessments that's created, and identifies fairness as a validity issue to the extent that it threatens whether we're making appropriate use of instruments or tests. Now, in the case of MathNation or the like, you know, it's not the test in itself necessarily, but it's rooted in aligning with an end of course exam. The problem is there's sort of this paradox where the standards primarily work with, you know, something like standardized or non-personalized learning and assessment, where the ideal is to treat everybody as if they're the same, cover all content, test everything, etc. Usually there's very little feedback to the student, though that's not necessarily always true, because sometimes that were, you know, formative assessment still in the realm of standards. Alternatively, personalized learning and dynamic assessment takes this different track, that testing should be a mediator facilitating student-centered instruction. And where you treat everybody as if they are the same, it ignores important facts about students, but it sort of sets up a conflict in that in the standardized, non-personalized sense, there's this universal idea that everybody should have equal opportunity to learn, whereas personalized learning changes that. So the standards don't take give you a lot to work with necessarily with opportunity to learn. It's not necessarily well defined, but what it does identify is that opportunity to learn is a fairness issue. When basically an authority provides any sort of differential access to opportunity to learn for some individuals, and then they hold those individuals accountable for instance taking an end of course exam, that's not fair. It's a test of validity. So the thing is, there's been a lot of debate in this area, as one can imagine, from long before this sort of online personalized learning existed. And one of those key debates is mastery versus coverage, where mastery is sort of this idea that opportunity to learn revolves around whether students have the opportunity, to use the term in the definition, to master content, and then coverage is simply whether students have seen the content or been exposed to the content in some way. And that's obviously an oversimplification of the debate, but we're, for the sake of argument, for the sake of starting at least this discussion, we're taking at least a look at the coverage debate. That might be more relevant in the realm of standards. But as one can see, the personalized learning puts students on different content paths. And then content exposure is going to vary across students at any given time. But there's an end of course exam administered at a single point in time. And then there's differential opportunity to learn, which introduces bias and validity concerns, at least according to standards, given that one framework for fairness. So we sort of have this idea as we're working through this, that we'd like to add to the literature sort of an empirical investigation of this discussed but understudied disconnect between personalized learning or personalized instruction and these accountability systems, which I know is a bit of a switch from our prior presentations. And this is, I guess, trying to glue these things together. And we wanted to provide recommendations for the future of accountability in a world of personalized learning, and also generate some tools and methods that can be used by various teams to improve recommender systems. So just to give you a sample of some of our study questions, which won't go through in too much detail, but effectively we started out with, well, given coverage as our main point, what are the differences in Algebra 1 content exposure at the time of an end of course administration in a very hypothetical, idealized situation, which all content is delivered via VLE? And compare that to a hypothetical group of students who did not receive personalized instruction and have these different learning scenarios where students may or may not learn. And we also varied things like student abilities. And we did this via computer simulation where we've seen those flowcharts that are sort of both in Corinne's presentation and Walter's presentation. And we effectively just simulated students through that flowchart. Now, what that allows us to do at least is, and I don't want to get into details here, but just show you what sorts of results and things we can think about, which is the different student routes through given sections of Algebra Nation. So what we see here are basically the total video views for each recommendation in a given section of Math Nation. And what you can see is there's a variety of paths students may take. And what this also tells us is teachers may get students that have been exposed to different content. And also at the end of the day, depending on the amount of time students have spent in Algebra Nation, obviously we've had to make some assumptions. There's going to be varying levels of engagement here with the content. And again, not to get into the details, but what we can see is that depending on the actual, depending on sort of the scenarios we're working with, there's very different content exposure where the moving bars show the proportion of content that people see in each section, which is on the x-axis of Math Nation, and then the proportion is on the y-axis. So what are some of our findings? Well, hypothetical students using personalized learning systems are generally exposed to less content, which isn't groundbreaking, but I think exposing the sort of logic of the system is very important. It's the implications of what we're trying to create. There's a lot of design features of the personalization system that influences content exposure though still. So, we're moving forward, we need to sort of think about integration of a VLE with something like an end of course exam, because this may or may not be considered as fair by different philosophies and stakeholders. But also just for the sake of this simulation, this work, having more information on realistic assumptions, of course, will always be helpful. So it's sort of a chicken or the egg problem. Anyway, thank you. My name's Daniel Katz, that's my email. And again, very much, I owe a lot of thanks to Corinne and Walter for helping me so much. All right, thank you.
Wonderful, thank you very much. All right, a quick moment for any questions. Really appreciate that presentation. All right. While we're waiting any questions, we are approaching time. So we might be going into overtime here, but perhaps we can think about it like a baseball game. You can't finish the game without the 9th inning here. And so coming in the bottom of the 9th is going to be Chenglu Li, a doctoral student at the University of Florida, who is going to be presenting on Fair AI in virtual learning environments. And Danny, you'll see a question for you from Jim in the chat that you can go ahead and respond to. And I will turn it over to Cheng Lu.
All right, thank you, Philip. Let me share the screen. Can you all see the screen okay? Okay. All right. Thanks for joining today. Our presentation is, oh, wait a sec. I think I opened the wrong. Oh, okay. Big thanks to Dr. Lichit for giving me this opportunity to do the presentation. I'll present our work on fair AI in virtual learning environments, supported by my advisor, Dr. Wan Lixing and Dr. Lichit. So we are living in a world of big data nowadays. The digitalization of education also embraces and expedites the use of big data to support teaching and learning. This big amount of data also enables researchers to explore statistical, machine learning, and deep learning models to support teaching and learning automatically. However, one major issue in current works of AI in education is that little is known whether these AI applications are fair. It is possible that a student course grade prediction model is twice as likely to incorrectly predict African-American students with a high risk of failure than their Caucasian classmates. And this unfair prediction can result in over intervention and other undesirable properties towards African-American students compared with their Caucasian counterparts. So what can we do with all this AI bias? We can use a series of techniques in fair AI to evaluate and even reduce the bias in our models. To give you some background, biased models are not uncommon in our life. In education, in a study of Risey and Singbeck in 2019, they reported that machine learning models could favor students without disabilities extensively if researchers did not carefully examine the models. So to reduce AI bias, we can use some techniques in fair AI. Generally, there are three families of techniques in fair AI: pre-processing, algorithm modification, post-processing. In our studies, we mainly examine strategies in algorithm modification, which usually modifies the loss function of existing machine learning models. So enough introduction, what have we done? We have conducted a study to build models that can predict students if a student will pass or fail in incoming assessment on Algebra Nation. This study uses upper level high school students' data on Algebra 2 from Algebra Nation with 2,700 assessments and 700,000 log data. So now you might wonder, how do we define fairness in our work? We're using a metric called equalized odds to evaluate fairness, which is a widely used metric in fair AI. So the equalized odds requires two things: an equal true positive rates across groups, for example, female and male, and an equal false positive rates across groups. So the equalized odds score will be the max difference between FPR and TPR. To ensure the AI fairness, we developed a fair logistic regression model by following the Seldonian framework of fair AI, which defines a procedure to ensure fair AI fairness. To put it simply, the fair logistic regression model allows researchers to define a series of constraints such as maximum equalized odds, as well as a confidence level that the constraint will be met. Then the model will not only just minimize the learning loss, but also try to satisfy our fairness constraints such that the trained model is fairness aware and tends to not overestimate or underestimate a student with certain demographics. So in the experiment, we compare the fair logistic regression with other commonly used machine learning models such as logistic regression, support vector machine, and random forest to evaluate the prediction accuracy and fairness. Here's the predictive accuracy of the models. We can see that random forest is the best performed model, which makes sense as its ensemble feature tends to boost predictive performance. However, we can also see that the fair logistic regression can achieve comparable performance. It is worth noting that the fair logistic regression can achieve similar and even slightly better performance than its direct counterpart, logistic regression. And here's the equalized odds scores for the model's fairness. The left one is for race and the right one is for gender. Smaller bars indicate fairer results. The deep blue bars are fair logistic regression. And the light blue and greenish bars are for the benchmark models, you can see that when it comes to gender, when it comes to race, a fair logistic regression with different equalized odds constraints can achieve the fairest results among all the benchmark models. For gender on the right-hand side, we can see that random forest achieves the fairest results, and the fair logistic regression shows a very similar results. Here we can see that it is possible that a fairness unaware model, such as the random forest, can be both accurate and fair. However, an important thing to note is that the fairness unaware model, the random forest, for example, does not guarantee fairness. In our case, the random forest is not that fair in terms of race, but fair for gender. So obviously, you might not want to rely on luck to have a fair model. And that's basically it for the presentation. Any questions?
Thank you very much, Cheng Lu. We've had a tried and true audience for the entirety of the presentation. Obviously, we want to invite any questions for the presentation on fairness for a moment or two. All right, there is a lengthy one here. Oh, this is a response to Jim's question from Daniel Katz. Any questions for Cheng Lu?
Cheng Lu, let me ask you something about the different ways of handling fairness. Obviously we did this research on the algorithm base, but do you know how it compares with the pre-processing? Does working on the algorithm perform better than pre-processing the data?
Well, I haven't tried the pre-processing and also the post-processing algorithms to compare with the algorithm modification. And but I think the main reason that we chose algorithm modification is because we don't want to change any of the data, and we don't want to change the model's predictions. So for pre-processing, you're basically resample the data to somehow eliminate the bias in your data. For example, to eliminate the information embedded within gender or race, so that the model can learn fairly. And for post-processing, it's basically just modify the model's prediction. And that's something that we don't want to do yet. So that's why we haven't compared that. But that's a really good question. I think it would be worth investigating, like to see how the performance will be in these three families of techniques.
Thank you.
And Cheng Lu, there's a comment for you in the chat. Just says the other categories it would be nice to de-bias are age and neurodiversity status.
Oh, what does neurodiversity mean here? Can you clarify,
Jim? You want to respond?
Sure. It's the mental health conditions in some cases. For example, somebody who's mentally ill might be considered neurodiverse and along, for example, a psychotic spectrum or something like that. Or just people who are developmentally disabled is another neurodiversity status that we tried to address. And of course, I was discussing with Danny the question of socioeconomic class, which is one of the more important ones lately.
I see, thank you. Yeah, we actually have tried other categories such as SES. We haven't tried the age because basically the students are in the same grade level and they are having the similar age. But it will be really interesting to see the neurodiversity as you suggested. Thank you.
Wonderful. So I'm going to pitch it back to Walter Leachy as our fearless leader and principal investigator, who you may have seen has his hand in a number of these different projects for any concluding thoughts. But I do see one more chat in there for you, Cheng Lu, if you want to respond to the question in regards to multiracial and indigenous students. But Walter, did you have any concluding remarks for the group?
Yes, I think the beauty of this short presentation format is that you were able to see the diversity of research that's occurring in the virtual learning lab. We used our MathNation as the platform because it was convenient to us. It was jointly developed by the Lessinger Center for Learning, which Phil directs, and StudyEdge, which is a private company. But the conclusions that we are getting from this research using MathNation is expected to generalize to other virtual learning environments. And as you know, they have becoming more and more popular, had an explosion of use with the pandemic. So, for us, we are fortunate that we had very extensive access to MathNation. For other platforms, it's hard to get, particularly the ones that are 100% private. It's hard to get research access. We are interested in partnerships. If you would like to do some research with us, we are more than happy to talk to you in any of these research fronts. So you have a bunch of emails from the chat, but also the virtuallearninglab.org website has a complete list of publications. Yeah, we would be happy to talk to you if you would like to collaborate with us.
Walter, I think that's a wonderful note on which we can end. We certainly invite continued conversation and collaboration in the MathNation, as well as our Flamingo platform, and certainly would love to investigate research possibilities to continue this. Also want to just invite you as we close out to continue the conversation in the chat. If you had another moment and wanted to continue, I would certainly invite you to pop into the chat any last thoughts, comments, or questions that you might have. If you have any ideas for future research, we would certainly love to hear from you. As Walter mentioned, we have our website here. It's virtuallearninglab.org. And then we also have Walter's contact information for you. And so I want to thank you very much for making our happy hour on the East Coast very happy, and wonderful to have you join us. And so look forward to hearing from you more and collaborating. So thank you very much. Have a wonderful day.
Thank you all.
Bye, everyone. Thanks for coming.
Ta-da.
Bye, thank you.